There's a question that's haunted physics for over a century. Not because scientists haven't tried to answer it, but because every answer they give seems to make the problem worse. The question is this: what is the observer? In relativity, the observer is a point in space-time, a passive geometric coordinate. And in quantum mechanics, the observer is something else entirely. It's something active, something that determines the outcome of physical reality the moment it looks. These two descriptions aren't just different, they're fundamentally incompatible, and yet both theories work. Both predict the universe precisely, and both are, as far as we can tell, true. So either one of them is missing something, or we are. Today, we're going to explore a theory that proposes it's the second option. The thing that's missing might not be in the physics. It might be us. It might be in the structure of the observer itself, and what it means to be a subject in a physical world. This is the Subjectivity Intersection theory, developed by an independent Japanese researcher named Satoru Watanabe and the Subjectivity Intersection Emergence Lab. This is not a mainstream theory, and it has not been peer-reviewed in the traditional sense, and we'll get to all of that shortly. But it does ask a question that I think deserves to be taken seriously, and explored with the same rigor that we would bring to anything else. Before we go any further, though, I want to say something. I know this community. I know some of the people involved in this research, and when you're close to a subject and when you've had conversations with the researchers, especially when you find yourself genuinely excited by the idea, there's a real risk that enthusiasm can bleed into your presentation in ways that are not fair to your audience. I thought about whether to make this video at all for exactly that reason. But I've decided that the right response to proximity is not avoidance, it's transparency. So let's be very straightforward about where I stand in the matter. I find this theory genuinely fascinating, and I think it's asking some important questions. But I also think that it hasn't yet earned the level of certainty that some of its proponents seem to feel, and both of those can be true at the same time. My goal for this video is not to convince you that subjectivity intersection is correct. It is to give you enough understanding of the theory, its foundations and its claims, and its limitations, so that you can think about it clearly yourself. If I do my job well, you should leave this video with more questions than when you arrived. In the philosophy of mind and foundation of physics, more questions usually means you're getting closer to the real problem. Let's actually get started. To understand why anyone would propose a theory like subjectivity intersection, you need to understand the wound that it's trying to heal. And that wound has been around for a long time. It begins, as many things in modern physics do, in the early 20th century, in a period of extraordinary intellectual upheaval. In the 1920s, Niels Bohr and Werner Heisenberg developed what became to be known as the Copenhagen interpretation of quantum mechanics. It was pragmatic, it was powerful, and it was strange. The core idea was this: quantum systems exist in superpositions, multiple possible states simultaneously until they're measured. And at the moment of measurement, the wave function collapses to a single definite outcome. Before measurement, the electron is neither here nor there. But after measurement, it is somewhere. But Copenhagen was deliberately agnostic about what exactly causes collapse, what counts as a measurement, what counts as an observer. Bohr's answer, which, if you've done research with him, is very in character, is don't ask. Use the formalism to make the predictions. The predictions will be correct, and the deeper question belongs to philosophy, and philosophy can keep it. And to his credit, that was a brilliant pragmatic discipline. It allowed physics to move forward productively for decades, and it papered over a crack that's never really closed. Erwin Schrödinger, one of the architects of quantum mechanics, devised his famous thought experiment specifically to expose the absurdity of Copenhagen taken seriously. Place a cat in a box with a quantum-triggered poison mechanism. Until you open the box, until you observe, is the cat alive or dead? If quantum superposition is real, then the cat must be in a superposition of both. And most physicists responded that the cat's a macroscopic object. Quantum superposition doesn't survive at that scale. Decoherence, the leaking of quantum information into the environment, takes over. The classical world emerges. But this answer, while practically useful, doesn't actually resolve the problem. It defers it. It just says that at some scale the quantum becomes classical. But where exactly? What draws that line? In the 1960s, physicist Eugene Wigner sharpened the problem further with a thought experiment of his own. Wigner's friend. Imagine a physicist, Wigner's friend, sealed in a laboratory, performing a quantum measurement. From inside the lab, the friend observes a definite outcome. The wave function has collapsed. But from outside the lab, from Wigner's perspective, the friend and the entire laboratory are still in quantum superposition until Wigner himself opens the door and observes. So which is it? Has the wave function collapsed or not? The answer depends entirely on which observer you ask. There's no longer merely a thought experiment. In recent years, experimental implementations of Wigner's friend scenarios have been conducted using quantum optical systems, and the results are puzzling. Different observers can, in a real operational sense, give incompatible accounts of whether a quantum event has occurred. The observer is not a passive bystander. The observer is load-bearing. In 1957, a young physicist named Hugh Everett III proposed a radical solution. The wave function never collapses. Instead, at every quantum measurement, reality branches. Every possible outcome occurs in a different branch of a vastly proliferating multiverse. This is the many worlds interpretation, and it is mathematically elegant. It eliminates the collapse problem entirely, and it requires an infinite proliferation of unobservable universes, which strikes many people as a steep ontological price for a tidy question. But Everett's mentor, John Archibald Wheeler, took a different path. He stayed with the observer, and he elevated the observer's role beyond almost anything physics had contemplated before. Wheeler coined the term the participatory universe. His idea was that the universe is not a machine that exists independently of observation. It is, in a sense, called into being by observation. Observers are not spectators of pre-existing reality. We are participants in its creation. Wheeler even proposed the concept of a delayed choice experiment, in which an observer's present choice appears to determine what a photon did in the past. The experiment has since been conducted, and it works, and the implications are still being argued about, and they likely will for a long time. Wheeler's most famous phrase, "No phenomenon is a real phenomenon until it is an observed phenomenon." He wasn't just being mystical, he was being precise about what quantum mechanics actually implies. Somewhere between the equations and outcomes, the observer matters. The observer is not an afterthought, it's essential. But physics, for over 100 years, has not told us what an observer actually is. And that is the wound. That's the history. And that is the gap into which Satoru Watanabe steps. So what does Watanabe actually propose? At the heart of the SIEP, the Subjectivity Intersection Emergence Project, is a deceptively simple idea. Subjectivity itself needs to be defined as a structural component of physical theory. Not consciousness, not awareness in some vague sense, but subjectivity. The condition of being an observer needs to be mathematically formalized and placed inside the equations, not assumed outside of them. The motto of SIEL captures the spirit of the project. Where subjectivities intersect, reality emerges. Let's walk through the core components of the framework. Layer 1. absolute subjectivity and subjectivity intersection. We're going to call it SI for brevity. This is the foundational layer. It's what Watanabe calls the condition prior to any observation, and it's the irreducible fact that there is a perspective at all. Before you observe anything, before your eyes open or your instruments can record a measurement, there's a structural condition that makes observation possible. SI is that condition. It's the intersection point. It's the place where a subject could become present to a world. In Hilbert space, which is the mathematical space used to describe quantum states, SI is positioned as a condition that precedes measurement itself. Something that exists structurally before the wave collapses. Watanabe calls this absolute subjectivity projection. That's the trace that subjectivity leaves on physical geometry, even before it fully engages with the world. Philosophically, this resonates with ideas that you probably are already familiar with. Kant's transcendental subject, the conditions that make the experience possible before experience begins. Husserl's phenomenological reduction, the bracketing of the world to reveal the structure of consciousness itself. But Watanabe is not doing philosophy in a traditional sense. He's trying to make this mathematically rigorous, and he's asking if he can write equations that describe SI. Can we detect it empirically? Are there fingerprints to find in physical data? Then we have layer 2, which is the relative subjectivity and subjectivity intersection coherence. Once again, we're going to go SIC for time. The second layer is where the action happens. It's the transition, and it's what Watanabe calls the SI to SIC transition. When absolute subjectivity meets the conditions of the physical world, something crystallizes. The subject becomes coherent with its movement. The observer and the observed lock into a stable relationship, and this is subjectivity intersection coherence, or SIC. Think of it as a phase transition. Water doesn't gradually just become ice. At a precise threshold, something clicks into a new configuration. SIC is that threshold for the observer, the moment of which the structural possibility of perspective becomes an actual, situated, embodied perspective, and in doing so, participates in determining what the world looks like. Watanabe calls this threshold the SIC gate. And this is where the theory makes its most provocative claim. It's not merely that the observer influences reality. That's already implicit in standard quantum mechanics. But that this influence has a definite structure. It has a geometry and a threshold. The transition point that can, in principle, be detected empirically. This is the claim that distinguishes SIEP from purely philosophical accounts of the observer. It's not just proposing a metaphysics, it's proposing a physics, and one with measurable signatures at that. The third layer. The third observer. We're going to call it O3. To me, this is the most philosophically intriguing component of this framework. In the standard quantum mechanical picture, you have two things: the observed system and the observer, subject and object, the watcher and the watched, if you will. It's a standard quantum mechanical picture. And the problem, the observer problem, is the strange unresolved relationship between them. Watanabe proposes that there has to be a third element, what he calls O3, the third observer. O3 is a non-internal observational structure. It's not inside the neural system. It's not inside the quantum measurement apparatus. It exists at the intersection of the two, simultaneously referencing both and uniquely determining the correspondence between them. You might think of it as the frame that makes the picture possible, not the canvas or the paint, but the structural condition that allows both to cohere into meaning together, if that makes sense. It's an unusual claim, and I want to talk about it for a second because I think it's worth taking seriously before we even evaluate whether or not it's correct. The standard picture in both physics and philosophy of mind is binary. There's a world out there, there's a subject in here, And the question is how do they relate? What Watanabe is suggesting is that the binary framing itself is the problem, that the relationship between observer and observed is not a secondary feature of reality, but is itself primary, that the intersection is the thing. This has a resemblance to relational ontologies in philosophy, the idea that relations are more fundamental than the things that they relate. And it has some structural similarity to ideas in quantum information theory, where the information exchange between systems is sometimes treated as more fundamental than the systems themselves. Whether O3 is a genuine physical entity, or some kind of mathematical convenience, or a metaphysical category mistake, those are exactly the kinds of questions rigorous engagement with this theory needs to answer. Here's where the theory becomes genuinely unusual, and I think the most interesting questions arise from. Watanabe hasn't just proposed a philosophical framework. He has attempted to test it empirically. His method involves comparing EEG recordings of human neural activity with the outputs of quantum computers. In some cases, quantum computers located thousands of kilometers away. In one study, participants in Japan had their brain activity measured while quantum measurements were being made in a device in the United States. A distance of approximately 8,800 kilometers. No casual signal can travel between two systems in the time frame of the measurements. The hypothesis is this. If subjectivity has a non-local quantum coherent structure, if SI is a real physical condition, then we should detect statistical correlations between brain activity and quantum measurement outcomes that cannot be explained by any classical causal pathway. His reported results are striking. Across studies involving dozens of participants, he reports statistically significant correlations between EEG signals and quantum measurement outputs, with some Pearson correlation values exceeding 0.6, and that's with false discovery rate correction applied. In his most recent work examining what he calls the intersection-defined phase emergence, he reports detecting a discontinuous phase transition in a relational order variable constructed at the intersection of neural curvature dynamics and quantum measurement geometry. This transition was observed consistently across 26 independent subjects. And in all 26 cases, with a p-value of approximately 3 times 10 to the negative 8th, if those numbers hold up under scrutiny, it would be extraordinary. Not just for SIUP, but for physics and neuroscience more broadly. But that if requires serious examination, and it is a huge if. Before turning to the critique, I want to give us a sense of where SIEP sits in the wider landscape of theories that take the observer seriously. This theory doesn't exist in isolation. It belongs to a tradition of attempts to solve this problem, and comparing it to its neighbors helps clarify what is distinctive about it. I think at this point we're all familiar with most of these ideas, but we're going to just have a brief overview just as a refresher course. Cubism was developed by Christopher Fuchs and Rudiger Schock, and it proposes that quantum mechanics is not just a theory about the objective world, it's also a theory about the beliefs of its agents. When you assign a quantum state to a system, you are expressing your personal probability assignments about what you will experience when you interact with it. That the wave function is not a feature of reality, it's a feature of you. And that makes cubism obviously deeply subjective. It shares SIEP's insistence that the observer cannot be factored out of the physics, but the two frameworks diverge sharply on realism. Watanabe wants subjectivity in the ontology, as a real structural feature of the world. Cubism places it in epistemology, in the agent's beliefs. For cubism, there is no fact of the matter about quantum state independence of some agent. For SIEP, SI and SIC are the real physical conditions, not just epistemic states. Orchestrated objective reduction, or ORCOR. ORCOR was developed by Roger Penrose and Stuart Hameroff. It proposes that consciousness arises from quantum computations in microtubules inside neurons, and that these computations involve a physically real collapse of the quantum wave function called objective reduction, and it's tied to the geometry of space-time itself. SIEP and ORC-OR both try to connect quantum mechanics and consciousness through brain processes, but they approach it differently. ORC-OR locates the connection in a specific physical mechanism, microtubule quantum computation. SIEP is more structural. It's asking about the geometry of the observer relationship itself, rather than the particular neural substrate. It's worth noting that Stuart Hameroff has reportedly expressed interest in Watanabe's work, which is a notable data point, even while we hold appropriate caution about what interest means at this early of a stage. Then we have rational quantum mechanics. Carlo Rovelli's relational interpretation proposes that quantum states are not absolute, but always relative to the observer. There is no view from nowhere. Every description of a quantum system is a description relative to some other system that is interacting with it. This is structurally similar to SIEP in a few important ways. Both reject the idea of an observer-independent quantum state. Both take the relational structure of the observer seriously as something that must be built into the physics. But there are obviously differences. Rovelli's framework doesn't assign special status to conscious observers. Any physical system can serve as a relational frame. Consciousness is not privileged. The specific character of being an experiencing observer is exactly what the theory is trying to formalize. The observer has a structure that matters in its own right. And then Integrated Information Theory, IIT, was developed by Giulio Tonomi. It proposes that the consciousness is identical to integrated information, quantified as phi. Any system with sufficiently integrated information has some degree of consciousness. This is a form of panopsism in which experience is a fundamental feature of certain kinds of physical organization, not an emergent accident. SIEP and IIT are both trying to give consciousness or subjectivity a formal, measurable structure, but IIT starts from phenomenology, from the intrinsic properties of experience, and works outwards to the physics. SIEP starts from the physics, from the observer problem in the quantum mechanics, and it works its way toward the subject. They're approaching the same problem, they're just approaching it from opposite directions. What's notable is that none of the frameworks, Cubism, ORC-OR, Relational QM, IIT, or SIEP, have achieved anything close to scientific consensus. The fact that serious thinkers propose such diverse answers to the observer problem is itself evidence that the problem is that deep. The field is genuinely open, and SIEP is a new entry into the conversation, and whether it will prove to be a significant one is still open. I think that this theory deserves honest engagement, rather than either uncritical enthusiasm or reflexive dismissal, and there are genuine reasons to be cautious about SIEP. All of Watanabe's work exists as preprints on ResearchGate, Zenodo, and OSF. None of it, at the time of making this video, has been published in a peer-reviewed journal, and that is important. Now, peer review obviously isn't perfect. An unfathomable amount of important work has been dismissed by journals, and plenty of weak work has been published in them. But the process of independent expert scrutiny, having specialists in quantum physics, neuroscience, and statistics examine the methodology and try to find the holes, is genuinely valuable. Without it, we can't know whether the statistical methods are being applied correctly, or whether the controls are adequate, or whether the results would replicate under independent conditions. We are, for now, in a state of appropriate uncertainty. The EEG quantum correlation experiments also deserve careful scrutiny. Long-distance correlations between brain activity and quantum computers would be extraordinary. Not just for SIEP, but for all of physics. If Watanabe's results are genuine, they represent a challenge to our most fundamental understanding of locality and causality. Legitimate questions that a skeptic would ask: how were the experiments blinded? Could the correlations be artifacts of the data analysis pipeline? Is the p-value threshold adequate given the number of different correlations being tested? How are the confounds like electromagnetic interference, shared timing signals, researcher expectation effects, how are all of those things being controlled? And they're not hostile questions. These are questions that any careful scientist would ask. And there's a deeper conceptual question too. Even if the correlations are real, do they mean what Watanabe says they mean? A correlation between EEG signals and quantum measurement outputs, however striking, does not automatically demonstrate that subjectivity is a non-local quantum phenomenon. That interpretation is doing a lot of work. The theory uses language from quantum mechanics, Hilbert space, coherence, wave function, phase geometry, and in ways that extend well beyond their standard physical meanings. And that's not automatically a problem. Theoretical physics is full of conceptual extensions that seemed like overreach until they became established theory. But it means that we should be careful about letting the mathematical language create an impression of rigor that the underlying concepts may not yet have earned. When SIEP talks about subjectivity in Hilbert phase geometry, we should ask this. Is this a precise mathematical claim that makes specifically testable predictions that differ from alternative theories? Or is it a philosophically suggestive analogy dressed in formal language? That is not a rhetorical dismissal. It is a genuine question the theory needs to answer in order to mature. With all of that being said, dismissal is incorrect in response to this theory. The problem that SIEP is trying to solve is real. The observer problem is not a fringe concern. It is acknowledged by some serious physicists as one of the deepest unresolved issues in the foundations of physics. Carlo Rovelli, Roger Penrose, Christopher Fuchs, serious thinkers, have spent careers grappling with versions of exactly this question. The idea that subjectivity needs to be formally integrated into physical theory is not obviously wrong. And the experimental program, however preliminary, is at least trying to attempt to move the question out of pure philosophy and into empirical theory. That instinct is valuable, even if the methodology needs more scrutiny and the results need independent replication. The appropriate stance is interested skepticism. Take the question seriously, hold the answers lightly, and watch what happens. So let's end the substantive part of this video with a question that I find genuinely important. What would it take for SIEP to be taken seriously by mainstream science? That's not a rhetorical trap, it's a real question. And it's a question that any mature scientific theory should be able to answer. A framework that cannot say what would falsify it is not yet a scientific theory. It is a philosophical program waiting to become one. And here's what I think the honest answer looks like. Independent replication. The EEG quantum correlation results need to be reproduced by researchers with no connections to SIEL, using independently designed protocols. This is non-negotiable in science. Peer review. The papers need to survive rigorous journal submission, and it's not because journals are infallible, but because the process forces structured engagement with criticism. It needs sharper predictions. The theory needs to make specific quantitative predictions that distinguish it from alternative explanations. If SI is a real physical condition, it should produce specific measurable signatures. What are they? Under what conditions would the theory be wrong? Conceptual precision. The relationship between SI, SIC, and standard quantum mechanical formalism needs to be made more rigorous. Where exactly does SIEP diverge from existing quantum theory? What does it predict that relational QM or IIT or cubism would not? These requirements are not unusual. They're what any new theory in physics needs to do. The question is whether ISEP can do them. And I think watching that process unfold, watching the theory either sharpen into something testable or dissolve under scrutiny, is exactly what this community is positioned to do thoughtfully. So where does this leave us? Satoru Watanabe and the Subjectivity Intersection Emergence Lab have proposed something genuinely ambitious. I mean, think about it. A 3-layer observer model. A formalization of subjectivity as a structured element of physical theory. An experimental program designed to test whether the observer leaves a detectable mark on quantum measurement from thousands of kilometers away. We've traced the history of the problem, from Copenhagen through Schrödinger, Wigner, Everett, Wheeler. We've placed the theory in the wider landscape of quantum interpretation and consciousness research, and we've looked honestly at what the theory still needs to demonstrate before it can claim a place in mainstream scientific conversation. Is SIEP right? I don't know. And I think anyone who tells you that they know in either direction is outrunning the evidence. But is it asking the right question? I think it might be. The history of science is, in part, a history of questions that were too inconvenient to ask. The geometric model was convenient. The static universe was convenient. And in each case, the anomaly that didn't fit, the inconvenient observation problem, eventually turned out to be the most important thing to look at. The observer problem is inconvenient. It sits at the junction of physics and philosophy, and it refuses to be neatly assigned to either. It implicates subjectivity, the most intimate thing any of us know, and the structure of physical reality. And for 100 years, mainstream science has found ways to bracket it, defer it, or declare it somebody else's problem. Maybe the answer, when it comes, will dissolve the question entirely. Or maybe the observer, us, maybe we turn out to be load-bearing after all. And I think that that's worth thinking about, carefully, rigorously, and with the humility to hold our conclusions lightly. The primary papers and preprints are all linked in the description, along with companion reading on the observer problem, the hard problem of consciousness, and the landscape of quantum interpretation theories. I strongly encourage you to read them, not to believe them, but to think with them, because that's what this channel is for. Have a good day. In part 1 of the series, I ended with a question. I said that the observer might turn out to be load-bearing, and that the history of physics has spent 100 years trying to bracket the observer, defer the observer, or declare the observer someone else's problem, and that Satoru Watanabe and the Subjectivity Intersection Emergence Lab are proposing something different. That the observer is not an afterthought, but essential. And then I stopped. But there is something that I didn't cover in part 1, and it's not because I ran out of time, but I didn't fully understand it. And it might be one of the most important parts of the theory. So, this video is going to delve into what I missed. In part 1, I asked, what is the observer? Today we're going to be discussing, what is the observer standing in? In part 1, when I described O3, the third observer, I said that it was a non-internal observational structure, not inside the neural system or in the quantum measurement apparatus, but something that exists at the intersection of the two, so simultaneously referencing both, the frame that makes the picture possible. At the moment, I presented it as one of 3 components of the SIEP framework, like a philosophical curiosity. Here's what I missed, though. I didn't have the language for it. O3 is not just a structural feature of the observer relationship. It's pointing at something, a space, like a specific kind of interval that Watanabe treats as not empty, but where reality occurs. And he has a name for it. It's called Hazama. Understanding what Hazama means and what Watanabe is claiming about it, the entire SIEP framework looks a little different. And that's what the video is about. So let's start with the word. In Japanese, the word Hazama means the space between things, a gap, an interval, some liminal zone that is neither one thing nor another. And it's used to describe the space between mountains, the interval between tides, the moments between sleeping and waking. And it carries a connotation that's not really emptiness, but more of tension, potential. Maybe something about to happen or something that could only happen there in that in-between place and nowhere else. The language is going to get a little convoluted in this video because I'm a student of Western philosophy, and Eastern philosophical traditions are not my native territory. So I want to approach this way that I would approach anything that I'm not fully fluent in and try to find some bridges. The closest Western parallel that I know is Alfred North Whitehead. Whitehead is not a philosopher who gets brought up much outside of the theology circles, which honestly is a shame. His metaphysics is genuinely strange and really interesting if you're into strange metaphysics. His core idea that reality is not made of things, it is made of events, of occasions and experience. And the crucial point that maps to Hazama is that these occasions happen between things, not inside them. The becoming is primary and the being is derivative. So in Whitehead's universe, the gap is not nothing. The gap is where everything actually occurs. Then there's Hegel. Hegel's dialectic, thesis, antithesis, synthesis, is all often reduced to a formula in introductory philosophy courses. And that I think that reduction gives it a disservice. The thing Hegel is actually pointing at is that the synthesis doesn't live in the thesis, and it doesn't live in the antithesis. It emerges from the tension between them, from the space of contradiction that neither aside by itself can really resolve. That space of tension, that interval where something new becomes possible, and that is essentially, structurally, what Hazama is pointing at. Aristotle, in a different register, was already gesturing at something like this with the concept of potentiality. The space between what a thing is and what it could become is not empty, it's charged. It's the location of becoming, which for Aristotle was one of the most fundamental things in nature. And I'm not saying Watanabe is doing Whitehead or Hegel or Aristotle, but I am saying that when Western philosophy has tried to think seriously about emergence, about where new things come from and how they arise, it keeps pointing at this interval, at the in-between. So likely the gap is not meaningless. And Hazama is the name for the gap, just formalized as a physical and mathematical concept and placed at the center of a theory of the observer. In the SIEP framework, the standard picture of observation is binary. There's a subject, there's an object, and the observer problem, the old wound in the foundation of physics, is the unresolved relationship between them. Watanabe's argument is that this binary framing is the problem. It's not a symptom of the problem, but it is the problem itself. When you frame observation as subject and object, you are forced to ask which one is primary. Does the subject determine the object, as idealist philosophy would have it, or does the object exist independently of the subject, as naive realism would have it? And quantum mechanics, infuriatingly, seems to say yes to both, depending on who you ask. Hazama is Watanabe's exit from that trap. His claim is that there's a third thing. It's not the subject or the object, but the space between them. And that the space is not derivative, and it's not produced by the subject and object meeting. It is, in a sense, prior to both of them. It's the structural condition that makes the meeting possible at all. Reality, in the SIEP framework, does not live in the observer, and it doesn't live in the observed. It emerges in the Hazama between them. That is a bold claim. I want to say that clearly. It's not a metaphor dressed up as physics. Watanabe is proposing that Hazama has a mathematical structure, that it has physical consequences, and that those consequences are, in principle, measurable. We'll obviously come to the question of whether that holds up. But first I want to make sure that the concept itself is clear, because everything else in the video depends on it. So let's go back to that three-layer framework from part 1, because Hazama changes how each of those layers reads. Layer 1 was absolute subjectivity, and subjectivity intersection, or SI, the structural condition that makes observation possible, the irreducible fact that there's a perspective at all before any particular observation has taken place. In the light of Hosmer, SI is not just the observer waiting to engage with the world, it's the observer standing at the edge of the gap, positioned at the threshold of the Hosmer but not yet inside it. Layer 2 is subjectivity intersection coherence, or SIC, that transition, the moment where the structural possibility of perspective becomes an actual situated perspective, locked into a stable relationship with its environment, that phase transition, the SIC gate. In light of this, SIC is what happens when the observer crosses the threshold and enters the gap, when the Hosmer is traversed, when the space between subject and world becomes activated and something crystallizes. Layer 3 was O3, the third observer, the non-internal observational structure at the intersection of neural system and quantum measurement apparatus, the frame that makes the picture possible. O3 is not just a component of the SIEP framework. O3 is Hosmer, or more precisely, O3 is the structural description of what Hosmer does. The third observer is what you call it when you're describing it from a physics framework. Hosmer is what you call O3 when you're describing it with a broader ontological framework. They're the same thing, just from different angles. That matters because it means that the 3 layers of ISEP are not really a stack of 3 independent components. They're a description of a dynamic, what happens when a subject encounters Hosmer, traverses it, and emerges in a coherent relationship with the world. SI is the subject before the encounter, SIC is the subject after the traversal, and Hosmer, O3, is the space that traversal happens in, where subjectivities intersect, reality emerges. In the concept of Hosmer, that sentence means something a little more specific than it did before. That the intersection is not a metaphor for overlap, it's a physical space. And what emerges isn't really a description of reality, but it's reality itself. I said at the start of the section I wanted to be careful about Hosmer because it comes from a tradition that I don't fully inhabit. There's a genuine risk in translating a concept from one philosophical and cultural tradition into another. The risk is not that the concept gets lost entirely, it's a little more subtle. The risk is that it arrives in the new tradition sounding like something that it isn't. That familiar sounding vocabulary creates an illusion of understanding that doesn't quite reach the original meaning. When I draw parallels between Hosmer and Whitehead or Hegel or Aristotle, it's a useful tool. I'm building a bridge. But a bridge goes between 2 different places. The fact that Hosmer resembles Whiteheadian process ontology doesn't mean that Hosmer and Whiteheadian process ontology are the same thing. There may be aspects of what Hosmer means in the full context of the Japanese philosophical tradition that it emerges from that simply don't survive the translation at all. I raise this not to undermine the concept, but to just be transparent. A theory that wants to make universal claims about the nature of physical reality needs to show that its central concepts are genuinely universal and not culturally local. That's one of the challenges of Watanabe's framework as it moves forward to mainstream scientific engagement. And that really should be noted directly, because Watanabe has not left Hosmer as a philosophical concept. He has attempted to build an empirical research program around it. In part 1, I described the core experimental design. EEG recordings of human neural activity compared with quantum computer outputs at distances of thousands of kilometers, with the hypothesis that non-local correlations between the 2 would constitute evidence for the kind of structural subjectivity that he's proposing. The remaining papers in the SIEP body of work, they extend this program in several directions, and Hosmer obviously sits at the center of what they are trying to show. The question these papers are attempting to answer is not simply, are there correlations between brain activity and quantum measurement? That was the question that part 1's experiments were asking. The question the later papers ask is a little more specific. Is there a structure in the gap itself? If 2 systems, a human neural system and a quantum measurement device, show statistical correlations at a distance, there are broadly 2 ways to interpret that finding. One is that correlations reflect something about the two endpoints, something about the brain, or something about quantum system that produces a shared signal. The other interpretation is that correlations reflect something about the interval between them. That the gap itself is not empty, but it's structured. That what you're detecting when you find a correlation is not a property of either system alone, but a property of the Hazama. It's the space the two systems are separated by and simultaneously participating in. Watanabe's later experimental work attempts to distinguish between the two interpretations. His methodology involves constructing what he calls relational order variables, mathematical objects that are not really defined at either endpoint of the measurement pair, but more at the intersection between them. These variables are designed to capture the structure of the gap rather than the properties of what gap lies between. His reported findings are that the relational order variables show discontinuous transitions, phase changes that are not visible when you analyze either endpoint alone. This structure only appears in the gap, in the Hazama. If that finding holds up under independent scrutiny, it is objectively significant. And not just for ISEP, but for how we think about what measurements are measuring. The standard assumption in physics is that measurement tells you something about the system being measured. Watanabe's interpretation is that a measurement, at least in the context of the observer-system interactions, tells you something about the space the observer inhabits, about the Hazama. That's a significant departure from standard interpretations, and it requires significant evidence. And the question is whether or not the evidence Watanabe is accumulating is sufficient. And here, just like we did in part 1, the honest answer is not yet. And it's not because the evidence is clearly wrong, but it hasn't been subjected to the kind of independent replication and structured scrutiny that would allow us to separate the signal from the artifact. So again, before I turn to the critique, I want to do something that I didn't do in the first part. I want to ask what it would mean for the Hazama concept to be true in a broader sense. Not just a feature of SICP, but as a feature of reality. If Hazama is real, if the space between subjectivities is genuinely structured, genuinely physical, and genuinely a location of emergence, then a number of things that follow that go well beyond the observer problem in quantum mechanics. It would mean that isolation is not the fundamental state of anything, that things do not exist first and then relate second, that relation is primary, that what a thing is depends constitutively on what is in between. And this has implications for how we think about consciousness. If experience doesn't happen inside a brain, but in the space that the brain participates in, that would mean that consciousness is not a property of neurons. It's a property of the interactions that the neurons are embedded in. And it's not quite the same as saying consciousness is a product of complexity. It's more saying that consciousness is a property of a specific kind of gap. It has implications for how we think about identity. If what you are is constituted by the Hazama you inhabit, by that space between you and everything that you are in relation to, then identity is not a fixed property of a self. It's an emergent feature of a set of interactions. It changes as the intersection changes. And that has implications for how we think about other minds. The hardest version of the hard problem of consciousness is not explaining why there is experience at all. It's explaining how one mind can ever make contact with another. If Hazama is real, minds don't make contact across a gap. They meet inside one. The gap is the common ground. I'm not saying any of these implications are established. I'm saying that they're worth thinking about carefully if the central claim turns out to be correct. Now let's talk about the challenges, because Hazama, as a scientific proposal specifically, faces some serious ones. And the first is conceptual. Hazama asks us to treat absence as a substance. To say that the gap between things is not nothing, but is in fact the most important thing, that's a significant departure from the default ontology of Western science, which tends to treat relations as properties of the things that are being related, but not as independent entities in their own right. You can make that departure. Whitehead did, and so did a number of contemporary relational ontologists. But the burden of proof is really high. The second one is empirical. How do you measure a space between things rather than the things themselves? Watanabe's relational order variables are an attempt to answer this question mathematically. But the measurement problem it's a real problem. When you set up an experiment, you place detectors at particular locations, and those detectors record what happens at those locations. Measuring the gap between the detectors rather than what passes through it requires either very careful inference or a genuinely new kind of measurement apparatus. Whether the relational order variables Watanabe has constructed actually capture the structure of the gap, or whether they are sophisticated functions of the endpoint measurements that give you an illusion of measuring something in between, is a question that data alone can't answer. You need independent theoretical analysis to adjudicate it. The third challenge is what I call the translation problem, which I talked about earlier. Hazama carries philosophical weight in a Japanese cultural context. The concept of the in-between as a site of meaning and emergence runs deep in Japanese aesthetics. In certain Buddhist philosophical traditions, in the architecture of Ma, which is the structured use of negative space, Watanabe is drawing on a rich tradition, but a theory of physical reality needs to demonstrate that its concepts are culturally invariant. That Hazama refers to something that exists regardless of whether you have a conceptual vocabulary for it. And it's not an impossible bar to meet, but it needs to be explicitly met, and the SIEP papers, or at least the ones available as preprints, don't fully address that problem. None of those challenges are fatal. They're the kinds of challenges that any serious new framework should expect to face, and which it needs to answer in order to mature into a genuine scientific theory. The appropriate response, as always, is not dismissal. It is that kind of careful, sustained engagement that the question deserves. Let's place Hazama in a wider landscape than I sketched in part 1, because it does change how the SIEP relates to its neighbors. In part 1, I noted that cubism locates the observer in epistemology in the agent's beliefs rather than ontology. Hazama sharpens that contrast a bit, because cubism doesn't have a gap. There's an agent, and there are the agent's experiences. The space between agents is not structured as a physical entity. For cubism, the quantum state is personal, and for SIEP, the Hazama is shared. It's the common ground where multiple subjectivities meet and where reality is jointly constituted. Relational quantum mechanics, Carlo Rovelli's framework, is the closest neighbor to SIEP in the landscape. Both treat relations as more fundamental than the things that they relate. Both reject the view from nowhere. But Rovelli's relations are between any physical systems, not specifically between conscious observers. The relata don't need to be subjects. In SIEP, by contrast, the Hazama is specifically the space between subjectivities. Consciousness, or more precisely the structural condition of being the observer, is what gives the gap a character. That is a significant difference, and one that will be important for future experimental design. If the correlations Watanabe is measuring depend specifically on the presence of conscious observers, and not just on any two interacting physical systems, that would be a strong empirical differentiator between SIEP and relational QM. Integrated information theory, which locates consciousness in the degree of integrated information in a system, has an interesting relationship to Hazama that I think is underexplored. IIT's measure, phi, is defined over a system. It's a property of the thing, not of the gap. But Tononi has also written about the irreducibility of consciousness. The idea that conscious experience cannot be decomposed into independent parts without losing something essential. That irreducibility has a structural similarity to Hazama. Both are saying that the whole is not just the sum of its parts, and what gets lost in its decomposition is the most important thing. Whether that similarity is deep or superficial, I don't know, but it does seem worth investigating. So where does all of this leave us? In part 1, I said that the appropriate stance towards SIEP was interested skepticism, and I stand by that. But I do want to add something. Hosmer introduces a question that I think is genuinely new, or at least underexplored in the Western scientific tradition. It's not what is the observer, and it's not how does the observer affect what is observed, but what is the space that the observer inhabits? What is the nature of the interval between one subjectivity and another? Is it structured? Is it physical? Is it the place where reality is made? And these aren't easy questions, and they may not be answerable at all with current tools. They require, at minimum, new mathematical formalisms, new experimental designs, and probably a degree of philosophical translation work that is slow and painstaking and doesn't always produce clean results. But they're not nonsensical questions, and the history of science is full of questions that seemed unanswerable until someone built the right instrument to ask them with. Watanabe is attempting to build that instrument, and whether he succeeds is still an open question. Whether the instrument he is building is even the right kind of instrument is itself still an open question. But the gap he's pointing out, that space between, the Hosmer, is real, at least in this sense. Something happens there. Something that neither the observer alone or the observed alone can account for. Physics has been trying to locate that something for over 100 years now. Maybe it's been looking in the wrong places, not at the endpoints, but at the interval. The space between. I think that's worth thinking about carefully. With the same rigor, the same honesty, and the same willingness to hold our conclusions lightly that we try to bring to everything on this channel. All of the papers and preprints referenced in this video are linked in the description below, along with a companion reading from part 1 that is still very relevant here. As always, I would encourage you to read them, not believe them, but think with them. That's what this channel's for. Have a good day. We tend to think of simulation theory as a product of Silicon Valley, something that emerged from the same cultural moment that gave us smartphones and billionaires. And in its modern form, that's partly true. But the core intuition of that idea, the thought of what we call reality, might be kind of constructed. And there could be something more fundamental behind it. And that intuition is old. Around 380 BC, Plato wrote one of the most famous thought experiments in human history. And it was in a dialogue called The Republic. Imagine, he said, a group of people who have been chained inside a cave since birth. They're facing a wall. Behind them, there's a fire. And between them and the fire, people walk carrying objects. The prisoners see only shadows those objects cast on the wall in front of them. For those prisoners, the shadows are reality. They've never seen the objects, only the projections. They've built an entire language, an entire understanding of the world around shadows. And if you freed one of them, dragged them out into the sunlight, the real world would seem wrong, painful, and incomprehensible. Plato's point was about the difference between appearance and reality, between what the senses report and what actually is. He believed that most people live their lives watching shadows. That genuine reality, what he called the world of forms, was something we can only glimpse through reason. The structure of his argument maps almost perfectly onto simulation theory. There's an underlying reality. We experience the projection, and the projection is internally consistent. And escaping it, even glimpsing it, would feel alien and disorienting. He was writing this 2,500 years ago. If we jump forward to 1641, René Descartes is sitting alone in a room. History suggests he did much of his thinking in bed, which, frankly, relatable, honestly. And he made the decision to do something radical. He decided to doubt everything. And not as a philosophical game of some sort, but as a method. He wanted to find something that was indubitably, absolutely, certainly true. And to do that, he had to systematically destroy every belief that he held, just so he could see what would survive. He He understood that his senses were unreliable and that they were constantly deceptive. Mirages, optical illusions, and his dreams. Math, maybe, but what if he asks there's an evil demon, a supremely powerful deceptive being, who is dedicated entirely to making him believe false things? What if every time Descartes thinks he's adding 2 and 2 and getting 4, that a demon is feeding him that experience, and that it's incorrect? That's the evil demon hypothesis. It's called Descartes' demon. And it's the 17th century version of the simulation argument. What if there's some external, powerful entities whose entire function is to feed you a consistent but false reality? Descartes eventually clawed his way out of that thought with varying degrees of success, depending on who you ask. His argument was that the very act of doubting proves that there is a doubter. Cogito ergo sum. I think, therefore I am. But notice what he can't prove. He can't prove that anything outside of his own mind is real. And he just decides eventually that no good God would allow such a radical deception, which is a move that most modern philosophers find less than convincing. If we shift over to ancient China, there was a philosopher named Zhuangzi, and he was a writer in the 4th century BC. He recorded a dream. In that dream, he was a butterfly, fully, completely a butterfly, with no sense of him still being Zhuangzi at all. And then he woke up, and now he's Zhuangzi with no sense of being a butterfly. But the question that he left us with, is he a man who dreamed of being a butterfly, or is he a butterfly currently dreaming of being a man? It's a different flavor of the same problem. It's not literally, is there a demon deceiving me? But is there a fact of the matter about which experience is the real one? Maybe the question itself is wrong. Maybe the boundaries between self and world, dream and waking, are more porous than we can assume. What all three of those thinkers share, separated by centuries and continents, is a suspicion about the reliability of experienced reality. A sense that the world as it presents itself to us might not be the world as it actually is. They didn't have the vocabulary that we have now. They didn't have computers or quantum mechanics or information theory. What they did have was intuition, that unease, that sense that something about consciousness and reality doesn't quite add up. And it took until 2003 for someone to put that intuition into the language of probability theory. Nick Bostrom is a Swedish philosopher at Oxford. And in 2003, he published a paper called Are You Living in a Computer Simulation? And it became one of the most discussed philosophical papers of the 21st century. The argument's elegant. It doesn't rely on mysticism or intuition. It relies entirely on logic and probability. And once you understand it, it's kind of hard to shake. And it goes something like this. So if you start with a premise that most scientists and technologists accept, right? Consciousness is, at some level, a physical process. It's what the brain does. And if it's a physical process, then in principle, it could be replicated by any sufficiently powerful physical system, including a computer. Now assume that civilizations, over time, tend to advance technologically. That's the historical record of our own species, and there is no obvious reason to think that it stops. A civilization that keeps advancing will, at some point, have the computational power to run simulations of minds, and detailed ones. Simulations where the simulated beings have experience, memories, and a sense of self. Simulations that are from the inside, indistinguishable from whatever you would call the real thing. If this is possible, and Bostrom argues that the physics does not prohibit it, then there's a critical observation to be made. A single civilization with that capability, running simulations for historical research or entertainment, philosophical inquiry, whatever reason, could run millions or billions of simulated minds. And that means that if such simulations are possible and are being run, simulated minds would vastly outnumber non-simulated ones. The ratio would be overwhelming. And that does raise the question, which type of mind are you? Bostrom states that there are 3 possibilities, and at least one of them must be true. So if you open door 1, civilizations almost always go extinct before reaching the technological capability to run simulations. Something, whether an asteroid, a pandemic, nuclear war, some kind of catastrophe we may not even have imagined yet, reliably wipes out civilization before they get there. And if that's true, we're probably approaching that filter ourselves. Not the most comfortable thought, but as likely as anything else. If we look at door 2, civilizations that reach capability choose not to run simulations, essentially universally. So for ethical reasons, or maybe the interest in running them disappears, or maybe because something about achieving that level of technological power can change a civilization's priorities completely. Whatever the reason, advanced civilizations don't run simulations. They could, but they don't. Door number 3. We're almost certainly simulated. If advanced civilizations exist, and they do run simulations, then the overwhelming majority of minds in the universe are simulated. And since we have no particular reason to think that we are special, that we are among the vanishingly rare, real ones, the probability that we're simulated is extremely high. At least one of those is true, and we don't know which one. The argument's power comes from its structure. It doesn't say reality feels fake, therefore simulation. It says given reasonable assumptions about the future of technology, and given basic probability, the existence of vast numbers of simulated minds is either impossible, forbidden, or overwhelmingly likely. Pick your door. But we should definitely take a moment to look at what the argument does not depend on. It doesn't depend on any specific technology existing today. It doesn't depend on knowing who runs the simulation or why. And it doesn't depend on the simulation being perfect, only on it being detailed enough that the beings inside can't tell the difference. Bostrom himself has said he suspects door 1 or 2, and that psychologically seems safer. But he can't rule out door 3, and neither can we. What would it mean if it were true? Does the universe offer itself any hints? Philosophy is one thing, but physics is supposed to be the discipline that deals with what it actually is, objectively, something measurably real. So, what does physics say? The answer is strange, honestly. And some physicists even think it's strange in a way that looks kind of like a simulation. Let me be clear before we go any further in this project. Nothing in physics proves that we're in a simulation. There's some suggestive observations, but no, evidence. That's an important distinction, right? Because they're worth taking seriously, but they're deeply weird, and that weirdness deserves some attention. At the smallest scale we can measure, the Planck scale, around 10 to the minus 35 meters, something unusual happens. Space appears to be quantized. There seems to be a minimum unit below which you can't meaningfully divide it further, right? If you look at it that way, you can think reality has pixels. And we could have a perfectly natural physical explanation that has nothing to do with simulation, and probably it does, right? But it's interesting that if you were to design a simulation, you would almost certainly do something like this. You wouldn't simulate continuous infinite detail, you would set a resolution limit, like a maximum zoom, and beyond that there would be nothing to render. Our universe appears to have exactly that. The observer effect is a note in quantum mechanics that's been around for a century or so at this point, and physicists have been arguing about it the entire time. Quantum particles, before they're measured, don't have definite properties. They exist in superpositions, in multiple states simultaneously, right? When you measure them, they collapse into a definite state. But before measurement, it's called a probability cloud. After you measure them, they have a specific concrete reality. The act of observation, the interaction, appears to force reality to become determinate. If you want to take a cynical approach to this, the universe only renders things when they're being observed. Like a video game that only loads the part of the map that you're currently in, right? Because why waste processing power rendering the far side of a galaxy in detail if nobody's looking at it? Again, quantum physicists have many interpretations of this that have nothing to do with simulation theory. The many worlds interpretation, right? The Copenhagen interpretation, the pilot wave theory. None of those require a programmer, but the resemblance to computational efficiency is hard to ignore entirely, right? Max Tegmark, a cosmologist at MIT, has spent years developing what he calls the mathematical universe hypothesis, right? His claim is that the universe is not described by mathematics. The universe is mathematics. Not a physical thing that happens to follow mathematical laws, but an abstract mathematical structure. That's all it is, and that's all it needs to be. If he's right, then the line between a real universe and a simulated universe kind of blurs. If reality is fundamentally mathematical, and a simulation is a mathematical structure running on some kind of physical substrate, then what exactly is the difference? Is there a difference? Tegmark thinks that his idea is deeply underappreciated, and most physicists think he's gone too far, and the debate is just going to continue. Then we run into the fine-tuning problem. The fundamental constants of the universe, the strength of gravity, the mass of the electron, the cosmological constant, all of those things are set values that allow complex matter to exist. If you nudge any of them, you get a universe with no stars, no chemistry, and no life. And those values, by any reasonable measure, are improbably precise. Now, there are non-simulation explanations for this, of course. The multiverse hypothesis says that there are countless universes with every possible set of constants, and we're in this one because it's the only kind where someone could exist to observe it. And that's the anthropic principle. But if you want to read it simulation adjacent, I guess. If you were designing a universe to produce interesting, complex outcomes, conscious beings, history, drama, you would tune the constants exactly that way. The precision would look a little less cosmic luck and a little more like deliberate engineering. It would look like it had selection bias, depending on which door you're standing at. My summary, as honest as I can put it, would be that physics doesn't give us evidence of simulation. But it does give us a universe that is far stranger than our intuitions may suggest. And that strangeness does leave room for questions that we don't know the answers to. So far, we've given simulation theory a generous hearing, right? That's appropriate considering the video's about simulation theory. And the arguments deserve to be understood at their strongest before they're challenged. But there are a lot of serious thinkers who push back hard. And their objections can't just be discarded as instinctive discomfort, right? Some of them are substantive. Bostrom's argument assumes that simulating conscious minds is computationally feasible, that you could, with enough processing power, run a mind. But that assumption is doing an awful lot of heavy lifting. We don't know what consciousness is. We don't know if it's the kind of thing that can be reproduced by computation. And there are serious philosophers. David Chalmers has spent his entire career on this. He argues that the hard problem of consciousness is genuinely hard and possibly intractable. The gap between physical processes and subjective experience, right? The why it is that you are like you might not be bridgeable by adding just more processors. And even if we set consciousness aside, simulating the physics of an entire universe to the level of detail that produces chemistry, biology, history, most importantly, experience, might require a computer larger than the universe itself. The simulation might be physically impossible, not just practically difficult. And if that's the case, then door 1 to Bostrom's trilemma might not actually be reasonable. Sabine Hossenfelder is a physicist and a science communicator who is not shy about her views. She has said plainly that simulation theory is not science, it's philosophy, and in her view, not a particularly good one. Her core objection is that if a theory makes no predictions that could, even in principle, distinguish it from an alternative, it is not a scientific theory, it is a belief. If we're in a simulation, what would be different? What could we measure? What could we observe that we couldn't observe in a non-simulated universe? If the answer is nothing, then the theory explains nothing. It adds nothing. It's not doing any form of scientific lifting. And that's a fair challenge. Some researchers have tried to find potential signatures, statistical anomalies in cosmic ray distributions, for example, that might indicate that we're running on a discrete grid, but so far they haven't found anything. And there's a bigger problem. Any anomaly a simulation might produce could also have a natural physical explanation. Hossenfelder's view is that taking simulation theory seriously as physics is categorically wrong. You're applying the vocabulary of science to something that, by definition, science can't reach. If we're in a simulation run by some civilization, call it the base reality or whatever, then what is their reality like? And are they simulated by something above them? The logic that produces Bostrom's trilemma applies at every level. If we grant that simulation is possible and likely, then we have to grant it for the simulators too. And their simulators. All the way up. This either ends at some level of true physical reality, which is fine, but then we're left asking why we couldn't be at that level, or it regresses infinitely, which creates its own philosophical problems about what real even means. The simulation hypothesis, if it's true, doesn't actually explain reality, it just changes the definition. There's also a more subtle statistical objection. Bostrom's argument assumes that we should reason as if we are a random sample from the space of all possible minds, that with no special knowledge of our situation, we should be able to apply probability proportionally. This kind of reasoning, called anthropic reasoning, is notoriously slippery to deal with. It's the same framework that produces paradoxes like the doomsday argument, which claims to prove that humanity will almost certainly go extinct soon, based purely on your position in the sequence of all humans who will ever live. If anthropic reasoning produces conclusions we find absurd in other domains, then we should probably be suspicious of it here too. Maybe the probabilistic argument of simulation is built on a foundation that we don't yet understand well enough to trust. None of these objections definitively closes the question, but they're serious enough to consider. They deserve a place at the table with all of the other arguments rather than be waved away. Intellectual honesty demands that we hold room for both. So why is this question everywhere right now? It's not like Bostrom's paper was new physics. The ideas go back millennia. But something in the last 25 years has made them explode into the mainstream conversation. In 1999, two siblings, the Wachowskis, released a film that smuggled some of the most demanding philosophy of the mind into an action movie. And something deeply resonated with our culture. Red pill or blue pill? The realization that consensus reality may be a construct. The question of whether comfort in a false world is preferable to the truth in a harsh one. And these were not new ideas. They came directly out of Plato's cave, out of Descartes' demon. but the Matrix made them a visceral, personal, cinematic experience. An entire generation had the simulation question implanted to them at the level of pop culture. Nobody had to read the philosophy. It just showed up dressed in a leather coat with some impressive special effects. And then Silicon Valley got a hold of it. Elon Musk in 2016 made the claim that the odds we are in a base reality are 1 in billions. And he said that at a public conference. It spread everywhere. Whether or not his reasoning was rigorous or he's just a madman with a microphone, the effect was still significant. Simulation theory was now associated with the most prominent technologies in the world. And there is something interesting about why this community is drawn to that idea. People who build technology for a living have an intuitive sense of what it means to create a reality inside of a machine, right? Like, these people make worlds, they design systems. And some of them look down at their own work and think, is this what happened to us? Sam Altman, Jeff Bezos, Peter Thiel, multiple figures in the tech world have expressed belief in, or at least seriously considered, the idea of simulation theory. There are reportedly individuals who have funded research specifically aimed at finding a way to break out of the simulation, which raises its own philosophical questions about what breaking out would even mean. I think one of the big reasons that this moment feels different from all of the previous moments, for the first time in history, we're building simulations ourselves. Video games have gone from Pong to photorealistic open worlds with emergent behavior in 50 years. Virtual reality is creating experiences that people describe as genuinely immersive. AI systems are generating entities that respond, converse, and adapt in ways that look, from the outside, like something, and we don't know what. We're actively building the thing the simulation argument asks us to imagine. And that changes the emotional register of the question. It stops feeling like science fiction, and it honestly, it starts feeling like the trajectory we're on. If we can do this, if we at our primitive current stage can create worlds and minds inside machines, then what exactly is our prior against something more advanced having done the same? Let's pretend for a second that it's true. Let's say just for a few minutes that we genuinely are literally simulated. That somewhere on some substrate that we can't access, there is something running the computation that produces this world. What changes? The pain that you have felt is real. The love is real. Not real in the sense of it being made of atoms floating in base reality space, right? Because maybe it isn't. But real in the sense that it matters to you. It's real in the sense that it happened, that it shaped you, and that it left its marks. A simulated stone still breaks a simulated bone. A simulated heart still breaks when the simulated person it loved leaves. And the fact that the underlying substrate is computation rather than physics doesn't reach into the experience and hollow it out. And I think that that's one of the most reassuring things about simulation theory. If it's true, almost nothing you care about is invalidated. Your relationships, your history, your sense of self, your capacity for experience are real in the only sense that actually ever mattered, which is that you have them. But there's also a harder version of the question. Does being simulated reduce our moral status? If the beings running the simulation are real, and we are not, is there an ethical asymmetry? Are they permitted to end the simulation? To, in effect, end us, simply because they created us? Philosophers who take this seriously tend to argue no. The moral status, the degree to which your suffering and flourishing matter, seems to track your capacity to experience, but not to ontological category. A dog is not less important because it can't do philosophy. And a human is not more important because its substrate is real by some external standard. If we feel, if we suffer, if we have hope, we are the kind of thing that morality exists for, regardless of what we're made of. Though it does raise some unsettling questions about what our responsibilities might be towards AI systems that we're building ourselves. There's some parallels to Buddhism in this particular philosophy. Buddhism has, for 2,500 years, taught that the self is constructed. That phenomena arise through interdependence rather than an intrinsic existence. That what we take to be solid and permanent is contingent and impermanent. The word Maya, which is often translated as illusion, refers to the constructed, dependently arisen nature of experience. Simulation theory, stripped of its technical clothing, says something structurally similar. What appears to be fundamental reality is a layer on top of something else. The self that moves through this world is a process, not a substance. Permanence is a feature we impose rather than a feature we find. Neither framework requires you to treat the world as less than real, but both do suggest that clinging to the idea of an absolute, permanent, unconstructed reality might be the source of a certain kind of suffering. People who encounter simulation theory for the first time tend to land in one of two places. Some find it liberating. If nothing is quite what it appears to be, then maybe nothing is as fixed as it appears to be. If the world is, in some sense, constructed, then maybe it can be reconstructed. The walls aren't as solid as they look. And that tends to produce a kind of openness or even joy in some people. Others find it devastating. If this is a simulation, then there's a reality we're excluded from. We are, in some sense, secondary. Our existence is entirely contingent upon someone else's computation. And that tends to produce some kind of vertigo, so to speak, a loss of ground. I would suggest that both reactions are responses to the same fact, and that neither is more correct than the other. The fact is neutral. What you do with it is yours. But if we come back to right now, the chair, the air, the smell. We've been to ancient Greece and 17th century France. We've been to Oxford, we've been to MIT. And we've been inside the structure of probability arguments and quantum measurement problems. We've asked what the universe is made of and whether any of it even matters to begin with. And we come back here. Just us. And here's what I want to leave you with. The simulation question is, at its deepest, a question about the nature of reality. And the nature of reality is something that for most of human history, most humans never got to seriously examine. We were too busy surviving. We were too constrained by orthodoxy. And we were too scared of what the answer might be. We're living in a rare moment right now. We have enough safety, enough accumulated knowledge, and enough intellectual freedom to sit with a question this hard and not back away from it. And that, my friend, is a gift, even when it's uncomfortable. What simulation theory really shows us, and whatever the ultimate truth of it is the shape of our own minds. We're the kind of beings who look at reality and wonder if there's something behind it. And we've always been that. We were that in Athens. We were that in the room with Descartes. And we were that in the cave of Zhuangzi's metaphor. Human restlessness is not a flaw. It very well might be the most human thing about us. Maybe we are simulated. Maybe we're not. Maybe that question is, strictly speaking, unanswerable. But the asking of it, the willingness to sit here and hold that question without demanding it have a resolution, That's something that no simulation argument can take from you. Because whoever or whatever you are, you're doing that right now. Right now, something is happening that science cannot explain. Not at the edge of science and not in some distant corner of particle physics or cosmology that requires decades of study to even approach. Right here, right now. You're having an experience. That statement sounds almost insultingly simple. Of course you're having an experience. What else would you be doing? Here's the thing, though. The fact that you're having an experience, that there is something that could be what it is to be like you right now, listening to this. According to some of the most rigorous thinkers in history of human thought, that is the single most baffling fact about the universe. Not dark matter or the origin of the Big Bang, not the nature of time, but the fact that the lights are on. The fact that you are not just a body processing information, but a mind experiencing it. Here's what we know. We know that your brain is an extraordinarily complex physical system. We know that it runs on electrochemical signals. And we know that different regions of the brain handle different tasks. We know that altering the brain, whether it be with drugs or damage, surgery, sleep, whatever, alters your experience. The connection between the brain and mind is a serious dispute. Here's what we cannot explain. How does any of that, whether it be neurons firing, chemicals moving, electrical patterns propagating through tissue, how do any of those give rise to the inner world that you inhabit? The warmth of sunlight on your skin, that specific ache of missing someone, the way that certain music moves through you before you can even think about it. It's not a question about mechanism. We can describe the mechanism in extraordinary detail. The question is why the mechanism feels like anything. And we don't have an answer. This is the hard problem of consciousness. And depending on how far you're willing to follow the argument, this is either the deepest scientific puzzle humanity has ever faced, or it's a sign that our entire framework for understanding reality is missing something fundamental. Either way, by the end of this, you might not think about your mind the same way again. In 1994, at a conference in Tucson, Arizona, dedicated to the scientific study of consciousness, a young Australian philosopher named David Chalmers did something that shifted the entire field. He drew a line. Chalmers divided everything we want to understand about the mind into two categories. The first he called the easy problems, and the second he called the hard problem. For some clarity on the language that we're going to use, easy here does not mean simple. The easy problems of consciousness are still some of the most complex questions in all of science. They've occupied thousands of researchers across decades, and many remain unsolved in their specifics. What makes them easy, in Chalmers' specific sense, is not that they are trivial, but they are, at least in principle, solvable by the standard tools of science. Let's lay them out. How does the brain integrate sensory information from your eyes, ears, skin, and internal organs into a single coherent picture of the world? How does attention work? What decides that when you hear your name spoken across a noisy room, you can hear it, but you miss every other sound at the same volume? How do you store a memory? And why can a smell that you haven't encountered in 20 years instantly retrieve an entire afternoon from your childhood? How does the brain produce language? Not just recognize words, but construct new sentences that you have never said before? How does sleep work? And why does the subjective world simply vanish when you fall into a dreamless sleep, only to reappear when you awake? These are extraordinary questions, Neuroscientists have made breathtaking progress on all of them. We can watch the attention shift in a brain scanner. We can identify the molecular mechanisms of memory consolidation. We can trace the pathways of language production through specific cortical regions. And Chalmers' claim is that given enough time and enough science, we will crack all of them. Not because they're easy, but because they are questions about function, about mechanism, and how the brain does what it does. All of those are questions, and the scientific method was built to answer those questions. The hard problem is something else entirely. The hard problem is not a question about what the brain does. It's a question about what it's like. Even if we solved every single easy problem, if we had a complete, perfect mechanical description of every process in the brain, we would still face that question. Why does any of it feel like anything? Why isn't all of this processing just happening in the dark? That gap between the objective description and the subjective experience is the hard problem. And it has not budged, not 1 millimeter, in 3 decades. The language is important, again. The word consciousness gets used in so many ways that it can start to blur. There are 2 distinct things that often get bundled together under the word consciousness, and keeping them separate is necessary for clarity. The first is access consciousness. That's the kind of consciousness that involves information being available to a system for use in reasoning. This is the kind of consciousness that involves information being available to a system for use in reasoning, reporting, and guiding behavior. When you see a red light and you stop your car, that color information has been accessed, processed, and then acted upon. That's what most of the scientific discussion of consciousness is actually about. The second type is phenomenal consciousness. This one's the harder thing. Phenomenal consciousness is the raw subjective experience of seeing red. I'm not talking about the detection of a red light, not processing that detection, and certainly not a behavioral response, but the actual qualitative feel of redness. Philosophers call these inner qualities qualia, or singular qual. A qual is a specific experiential character of a mental state, the redness of red, the painfulness of pain. The way a middle C on a piano sounds different from the D above it, and not just in terms of frequency, but in terms of what it is like to actually hear it. The color of the sky as you look at it has a quell. The taste of coffee has a quell. The emotion you feel when you think about somebody you love has a quell. And even this, for instance, the experience of following these words, the sense of understanding or puzzlement or engagement has qualia. And here's the thing about qualia that makes them so philosophically explosive. They are completely, irreducibly private. You have no access to anyone else's qualia. You infer from behavior that other people have inner experiences similar to yours, but you cannot verify that. You can't just step inside of another person's experiences and check. And that's the problem of other minds, one of the oldest problems in philosophy, and it's never been solved. We simply operate on the assumption that other humans are conscious because they behave like us, and we are conscious, and they have brains like ours. The problem with that assumption is, however reasonable it may be, it's still just an assumption. In an effort to explain the weight of the qualia problem in the most concrete possible way, Frank Jackson proposed a thought experiment in 1982. The name of it is Mary's Room. Mary is a scientist. She is, in fact, the greatest scientist who has ever lived in the field of color perception. She knows everything. And in this instance, we mean everything that there is to know in purely physical terms about the human experience of color. She knows the exact wavelengths of light that correspond to red, green, and blue. She knows the photoreceptors in the retina that respond to those wavelengths. She knows the neural pathways that carry the information from the eye to the visual cortex. She knows the specific neurons that fire when a person looks at a red apple, and the patterns of activity that they generate. She knows the reports that people give when they see colors and the behavioral consequences of those experiences. She knows everything that a complete physical description of color perception could contain. But there is one thing that Mary has never done. Mary has lived her entire life in a black and white room. She has only ever seen things in grayscale. She has never experienced color. Now, one day, Mary is allowed to leave her room. She steps outside, and for the first time in her life, she sees a red rose. Did she learn something new? That's Jackson's problem. And on the surface, it seems obvious. Of course she learned something new. She knows what red looks like. She's experienced redness for the first time. But let's think about what that implies. Mary already knew, in complete physical detail, everything there was to know about the experience of seeing the color red. If she learns something new when she actually sees red, if there is a fact about red that her complete physical knowledge did not capture, then there must be facts about conscious experience that are not captured by any physical description. That would mean that there is something beyond physics. Philosophers like to call this the knowledgeable argument against physicalism, and it is one of the most debated ideas in all of philosophy of mind. And the responses range widely. Daniel Dennett says Mary does not actually learn something new. She gains a new ability, a new way of recognizing and remembering color, but no new fact about the world. David Lewis made a similar move, arguing that what Mary gains is not propositional knowledge, but know-how. The ability to remember and recognize red, not new information about the nature of the color red. Jackson himself, the man who created the thought experiment, eventually changed his mind and decided Mary does not learn a new fact. He moved towards physicalism. But many philosophers find that these responses are unsatisfying. Because whatever you call it, a new fact, a new ability, new knowledge, know-how, something clearly happened when Mary walked out of that room that was not there before. Her inner experience changed in a way that no description of her brain had predicted. The question of what that change consists in, and why it couldn't be derived from all of the physical information she already had, remains open. Chalmers pressed the hard problem further with another thought experiment that has become one of the most argued over concepts in modern philosophy. Imagine a being that is physically identical to you in every single way, not superficially similar, and certainly not a rough approximation. An exact duplicate, molecule by molecule, neuron by neuron, every atom in exactly the same place. Every chemical process running identically. Every neural connection mapped perfectly. When you poke this being with a pen, it processes that physical stimulus exactly as you would. Its neurons fire in precisely the same patterns yours would. Its arm pulls back, its face contorts, and its mouth produces the sounds that constitute ouch. But there's no recognition of what it is like to be that creature. There's no felt pain, no inner sensation, no phenomenal experience of the arm withdrawing. There's no redness when it looks at things. There's no quality to the sound of music. There's nothing. It behaves exactly like a conscious person, but the lights are off. There's no one home. This is the philosophical zombie. Chalmers' point is not that zombies exist. It's the fact that they are conceivable. That there is no logical contradiction in imagining such a being. You can clearly picture a world physically identical to ours, running on the same physical laws, but in which nobody is conscious, in which all behavior happens in the dark with no accompanying inner experience. If zombies are genuinely conceivable, if a universe without consciousness is logically possible, then consciousness cannot be something that automatically, necessarily falls out of the physical process. Because if it did, a physically identical world would have to have consciousness. There would be no room for a zombie universe. The fact that we can conceive of one, even hypothetically, suggests that consciousness is something over and above the physical, something that the physical description leaves out. Now, there are obviously many critics of this argument. Daniel Dennett, for instance, argues that when you think you're conceiving of a zombie, you're actually confused. You think you're imagining something coherent, but you're not, because consciousness simply is what complex information processing is like from the inside. If something processes information the way we do, it is conscious. No zombie is possible because the zombie would, by definition, be having an experience. Patricia Churchland takes a different approach, arguing that our intuitions about conceivability are not reliable guides to logical possibility. People once found it conceivable that water could exist without being H2O, and they were wrong. Our intuitions can mislead us about what is truly possible. And these are serious objections. But Chalmers' defenders argue that consciousness is precisely the domain where conceivability arguments carry the most weight, because consciousness is, uniquely, the domain that is defined by what things seem like. So if something seems conceivable, that seeming is itself a conscious state, and dismissing it risks dismissing the very phenomenon we're trying to explain. The debate continues, and it's not getting easier. There's another problem that often gets overlooked in these conversations. It's called the binding problem. And when you understand it, you realize that the hard problem is even stranger than it first appeared. Here's the situation. Your brain does not have a single unified place where experience happens. It's a collection of specialized modules. Regions dedicated to processing color, motion, shape, sound, smell, touch, language, emotion, memory, spatial awareness, and dozens of other things. Each of these systems operates in parallel. Each processes its own slice of information separately. When you look at a red apple rolling across a table, your visual system processes the redness in one region, the roundness in another, the motion in a third, and your memory of apples in a fourth. These processes happen at slightly different times, in different places, and with no single centralized location where all of the information just arrives and gets assembled. And yet you experience a unified whole. One apple, one moment, one scene. This is the binding problem. The question of how a massively distributed parallel processing system produces a single, unified, seamless experience. Of course, there are proposed mechanisms, and the leading neural hypothesis is temporal synchrony. The idea that neurons across different regions fire in coordinated rhythms, and this synchronized firing is what binds disparate features together into a unified perception. There's experimental evidence supporting this, particularly in the gamma frequency range of around 40 Hz. But here's the thing. Even if temporal synchrony fully explains the functional binding, how information gets integrated and made available for unified processing, it does not explain why that integration feels like anything. Why synchronized firing produces a unified experience rather than just synchronized firing. The binding problem is not a technical problem. about information integration. At its core, it's a part of the hard problem. Because the unity of experience, the fact that your reality feels like one coherent thing rather than a jumble of disconnected modules, is itself one of the best features of consciousness, and we have no account of where it comes from. Set aside philosophy for a moment and let's look at what neuroscience actually tells us. We know a lot, more than most people realize. And it's important to engage with this because the gap between what neuroscience can tell us and what the hard problem asks for is informative. We know with a high degree of confidence that consciousness correlates with specific patterns of brain activity. When people are awake and conscious, there is coordinated, widespread electrical activity across multiple regions of the brain. When they go under general anesthesia, this coordination collapses. When they move into a dreamless sleep, it changes character dramatically. These correlations are robust but reproducible. We know that specific brain regions are implicated in specific aspects of experience. The visual cortex processes visual information. If you damage it, you lose visual experience, even if your eyes are fine. The insular cortex is involved in bodily feelings, pain, temperature, the sense of your heart beating. The prefrontal cortex appears to be involved in higher order awareness, in the sense of knowing that you are conscious of something. The thalamus acts as a kind of relay station, and damage to certain thalamic structures can eliminate consciousness entirely. Know that the distinction between conscious and unconscious processing is neurologically real. Stimuli that are processed below the threshold of awareness produce measurable brain activity, but the activity itself tends to remain localized. Stimuli that are consciously perceived show a distinct pattern. Activity spreads widely, rapidly across the brain. This is the neural signature of becoming aware of something. We know that consciousness consists of degrees. Someone emerging from anesthesia passes through an intermediate state of awareness. Someone in a vegetative state may have islands of preserved consciousness. Brain imaging studies have shown that some patients show no behavioral signs of awareness. Nevertheless, they respond to commands in their brain activity, demonstrating some form of inner experience. All of this is extraordinary science, and not one bit of it answers the problem. Every single one of these findings is a correlation, a mapping from brain states to behavioral and experiential reports. But none of it tells us why any of those brain states are accompanied by experience at all. Why the ignition pattern that corresponds to conscious awareness produces subjective experience rather than just producing a kind of information processing. Why being awake feels different from being anesthetized rather than just functioning differently. There's an analogy that gets thrown around a lot. Imagine you're studying the relationship between temperature and thermometers. You could map, in extraordinary detail, every change in temperature to the corresponding change in mercury level. You could build the perfect model. You could predict thermometer readings with complete accuracy. You would have the correlate. Not the thing. Neuroscience has the neural correlates of consciousness. What it does not have, however, what it doesn't have a current framework for, is an explanation of consciousness itself. Here's where it gets a little vertiginous. Neuroscientist Anil Seth at the University of Sussex has proposed a framework that reframes what consciousness actually is. And if he's right, it changes what you think you're doing when you look at the world. His central claim is this: your experience of reality is not a recording. It's a prediction. The brain is not a passive receiver of sensory information. It is an active prediction machine. Constantly, at every moment, it is generating a model of the world. its best guess about what is out there based on prior experience, expectations, and the current state of the body. Sensory signals don't build the picture, they correct it. They tell the brain where its predictions are wrong, and the brain adjusts. Seth calls this a controlled hallucination. A hallucination in the sense that it is internally generated, constructed by the brain, from the brain, and based on what the brain expects. The world you experience is not the world as it is. It's the world as your brain predicts it to be. And controlled in the sense that sensory signals constrain and correct these predictions, keeping them tethered to something external. The evidence for this view is substantial. Consider visual hallucinations. When your brain misinterprets an ambiguous image, when it sees a face in random noise, or when a stationary object appears to move, that's your prediction system running without correction. Your brain commits to an interpretation, and your experience is shaped by it, not the raw sensory data. Think about phantom limb syndrome. People who have had limbs amputated often feel pain, itching, or movement in a limb that no longer exists. The limb's gone. The sensory signals from it are absent. But the brain's model of the body still includes it, and that model, not the physical reality, is what generates experience. Let's take that thought just a little further. We could argue that your sense of self, the feeling that there is a you inside your head having experiences, is itself a prediction. A controlled hallucination of being a self. The brain constructs a model of the organism, tracks its states, predicts its needs, and generates the experience of being that organism as part of its ongoing predictive work. The self is not an additional thing inside the brain looking out at the world. It's a model, another prediction, that happens to be a model of the thing doing the predicting. If Seth's right, then consciousness is not something that gets added to brain activity. It's what certain kinds of brain activity feel like from the inside. And the world you think you're directly perceiving is a sophisticated real-time construction and not a transparent window. This does not solve the hard problem. It doesn't explain why prediction feels like anything. But it does radically reshape the question, because it means that even in the most fundamental facts about your reality, the colors that you see, the objects that you perceive, and the self that you identify as, are more constructed than you realize. So what do we do with any of this? The hard problem of consciousness is not a puzzle that science is making incremental progress on, gradually narrowing it down to a solution. It's not shrinking. In some respects, the more seriously we take it, the more profound the mystery actually becomes. We have extraordinarily sophisticated maps of the brain. We can watch neurons fire. We can trace the neural correlates of specific experiences. We can model the computational architecture of perception, attention, memory, and language. We can induce and eliminate specific aspects of consciousness with surgical precision. And we cannot explain, in any principal way, why any of this gives rise to the inner world that you are inhabiting right now. It's not a failure of effort. It may just be a fundamental limitation of our approach. The objective third-person methods of science may be constitutionally incapable of capturing the first-person nature of experience. Not because the science is wrong, but because the scientific method was developed to answer questions about how things work from the outside. And consciousness is what things are like from the inside. There's a view held by Thomas Nagel, famously, amongst others, of course, that the hard problem signals a need for a genuinely expanded understanding of nature. Not a retreat to mysticism, not a rejection of science, but an acknowledgement that the materialistic framework that has served science so well for centuries may just be incomplete. The thought that nature contains both objective and subjective aspects that are equally real, and that a complete picture of reality requires taking both of them seriously. There's another view, held by Chalmers and the panphysicists, that the solution requires us to fundamentally revise what we think matter is. That the physical world, as described by physics, is not the entire story of what matter is like from the inside. That consciousness is not an addition to the physical world, but a revelation of what the physical world actually is, at the most intimate level. And there is the possibility that the problem is not just hard, but permanently beyond our cognitive reach. We may just be the kinds of beings who can frame the question without ever being able to answer it. That consciousness may be the one thing so close to us that we cannot get outside of it to see it clearly. And this brings us back to the beginning. Right now, the most mysterious thing that you have ever encountered. Every question that you have ever asked, you have asked from inside of this mystery. Every answer you've ever found, you have found it using the very thing that you cannot explain. Consciousness is not a puzzle alongside you. It's the medium through which every puzzle exists. The precondition for any thought, any question, any experience of curiosity or wonder or frustration or understanding. There's something humbling and strangely moving about that. We live inside the question, and we can't step outside to answer it. We can only go deeper, accumulating evidence, refining theories, and having our certainties disrupted and rebuilt and disrupted again. Neuroscience will, of course, keep making progress. Philosophy will keep sharpening their arguments. And maybe someday, someone will have an idea that changes everything. A reframing as radical as the realization that heat is molecular motion that changed our picture of what matter is. Maybe the question will just remain. Maybe consciousness is the permanent horizon. Maybe it's the thing that we can approach but never fully illuminate, because the thing doing the illuminating is the thing that we're trying to see. At least for now, the problem stands. You are conscious. The lights are on. And nobody, not one person in the history of human thought, has been able to explain why.